a day off. So I'm going to, I have maybe 21 slides, but I have a video to start off. Like all technology, it doesn't work great. The video will show well, the audio does not. So I'm going to kind of talk my way through this maybe 1.5-minute video. Just gives a good overview of mag drive technology, and then we'll dig into it. The video shows a non-metallic aligned mag drive, which is one of many centrifugal technologies, but I'll just focus on the high and broad. So we'll start with that, and we'll go from there. So this is your centrifugal pump, obviously. So motor's connected to an outside magnet, right? So this is what we call the driven magnet, or I'm sorry, the drive magnet. So it's either keyed, in this case it's doweled onto the motor. And then you have a series of magnets in here. These happen to be neodymium iron. You can also get samarium cobalt. We'll talk about that in a minute. And on the other side, the driven magnet, you have the same material of magnets, and then you have them covered, either in a stainless layer or a non-metallic layer, because those magnets are in your pump fluid. So here's a good example of once you have magnetism between the outside and the inside set of magnets, now you have a coupled pump. So instead of using torque via a coupling, right, you're using magnetic flux between outside and inside magnet to drive the inside set of magnets. Now that inside set of magnets is attached to the shaft and to the impeller. Hence, now you have rotational speed of your impeller at the same speed that you have at your motor. So that's a good show right there. Now, in between the outside and inside magnets, you have a containment shell or a containment can. And that's really what your final barrier is between your process fluid, which is on the right side of that can, and your outside magnet, which is on the left side of that can. So you can see that that is your barrier right there. So everything to the right of that can, and the impeller and the casing, is subject to fluid, whatever you're pumping, and then everything to the left side is dry. So we'll X out of that, and then we'll go into this seminar. So this gives this is obviously a cutaway of another mag drive. This happens to be I think it's a FlowServe lined mag drive. But so I'll start over here on the left side. So you're attached to the motor here, right? A couple of bearings. And then right here is your outside magnet carrier. And then these black marks right here, and then up here, those are your magnets. Now they're not covered because they don't need to be covered because you're not protecting them from any fluid. They run dry. And then right here, your brown is your containment can or your containment shell here. And usually it's either gasketed or O-ring sealed, both up here and really right here, right at your face to your cover. That is what prevents any fluid, which is you see in the blue here, from leaking outside into the environment. Okay? So obviously what you do not see here, right, is any kind of coupling or any kind of mechanical seal. This shaft does not penetrate into the liquid end, right? It stops right here, i.e. magnetically coupled. So this, you send a magnetic attraction or a magnetic flux from your outside magnet through your can to your inside magnet. And this is a series of magnets. This magnet, or this magnet band, is attached to your shaft. Your shaft is attached to your impeller. So if this outside magnet is running at 4-pole speed, 1,800 RPM nominally, with current day magnets, both neodymium iron and samarium cobalt, there's no slip. So your inside magnet is also running at 1,800 RPM, and then you have rotational speed, right? So magnetic drives really, it's not so much a discussion about the hydraulics of a centrifugal pump, because they're generally speaking the same. It's how you are coupling and transmitting motor torque to the pump, and really then into the impeller and the liquid. Okay? 95% of magnetically coupled pumps operate in a very similar fashion. We represent a company called Innomag. This just gives a little bit of a breakdown of that video that you saw. So you have an outside magnet sending a magnetic attraction through that can. There you have an O-ring to an inside set of magnets. Now remember that again, those magnets in there are running in your process fluid, so they're coated either with a high alloy sheath or with a non-metallic coating. In this case, it's I think it's probably a Tefzel for Innomag, which is attached to your impeller and your casing, and you can see the lining there as well. Okay, so whether it's metallic or non-metallic, the concept is the same. This happens to be a flow-serve metal mag drive, so you can see this is all metal, no linings, but you see your outside magnet, right? Same concept, magnet carrier, outside magnet, containment can, which is now metal, okay? Inside magnet, and you can barely see that little red covering there. So that magnet is encapsulated, attached to your shaft, attached to your impeller. Same thing. Okay, that happens to be a metal mag drive. So why do you use mag drives? Typically, it's corrosives. Right? If it's any fluid that you really do not want seeing the environment, you can always use a mechanical sealing system to accomplish the same goal, but many customers prefer, I'd say, the relative ease that you can get with using a mag drive. There's limitations. We'll talk about that in a couple minutes. But anything corrosive, toxic, flammable, expensive. You may have a water-like fluid that's very easy to seal, but it's very, very expensive. So you may not want leakage purely for those reasons. You could use a mag drive. If you're concerned with emissions, even I think most on this conference call know by now, be with Frank Rottello's mechanical seal series, all seals leak. Even if it's vapor, they leak. So if it's highly corrosive or toxic and you have any kind of vapor leakage, you have an emissions issue. Another good reason you might want to go with a mag drive. Hard to seal fluids, expensive fluids, ultra pures. Okay, so a lot of different applications. If you're pumping 80-degree water, throw in packing or a single seal, and you're good to go. You're off to the races. So we'll talk about the pump construction, the magnets, the containment shell, bearings, jacking bolts. There's a lot of other features specific to each manufacturer, but we won't delve into the specifics. So really the history of mag drives started primarily with metal mag drives. I think that most of the development was in Europe, soon after in the United States. But really the material was mostly metallic because that's what sealed pumps were made out of. Typically at a minimum it's 316, but usually the corrosive nature of the fluid is such that you probably need a higher material of construction. So more than likely you'd see alloy 20 to minimum, or Hastelloy, and sometimes even titanium. Now with lined pumps, which really have become very popular in the last, I'd say, 20 years. When I started my career at Gould's Pumps, we had released actually metal pumps and non-metallic pumps, non-metallic line pumps. It's a cast iron shell, but then it uses a non-metallic lining. And what I have listed here are just many of the different linings that different pump manufacturers use, and they may use them for series or a variety of reasons. One, chemical compatibility is probably the most important driver, but it could be the relative ease or lack of ease in which you mold. It will mold and adhere to the casing, to the to the shell. There are even mag drive pumps that are fully non-metallic, so they're not lined, but they're fully non-metallic. And again, now you're forming a much larger block of non-metallic material, so that may drive your material selection. So there's a number of different liners. There's a number of different materials to use. It really is application and manufacturer specific. So I can't sit here and tell you that Kynar is better than Tefzel. There's areas that and liquids you would use Kynar, and there's liquids that you would want to use Tefzel. So this just gives you a little bit of a better view of a lined pump. You can see up here, that's actually a flat-faced flange, and then this right here is the roto-molded liner. And here's, obviously this is a sales piece, right, from Inomag. This is manufacturer X, and so depending on the manufacturer or maybe the application, you might see a little bit of this. So that's sometimes an issue that you might come up with when you're dealing with these line mag drive products. I think this is probably, being a sales piece, this is very rare, but because you are molding a liner onto a cast iron shell, the probability, albeit small, that may happen. So you can see the liner here and here. It's called roto molding. They basically put the non-metallic in as a powder, and they heat it, and they actually kind of really, I'd say, roll it in a machine under pressure in a mold, and then it comes out completely lined and completely adhered to the casing. And for most manufacturers, you can pull full vacuum. So if anybody has a concern about, you might be running a slight vacuum or a real low suction pressure application, and the lining actually coming off of the cast iron shell, that rarely, if ever, happens. Most manufacturers, Inomag, I assume ANSI-Mag, Flowserve, I assume Gould's, they probably all go to full vacuum. I certainly know that Inomag does. All right, so we talked about the materials, the overall materials. Now let's talk about magnets. There's really two types of magnets you can use, here and here, okay? And that's just one magnet block, which is probably the size, I'd say, of 2/4, okay? Neodymium iron is the magnet of choice, I'd say, in almost any industry. Neodymium iron is used, I say max 300. Some manufacturers would argue you can go up to 350, even 400 degrees, but I'm a little conservative. So once I get to 275, 300, then I move on to samarium cobalt. So neodymium iron is good for low to medium temperatures. It has generally similar torque carrying capabilities as samarium cobalt. So it's really not a horsepower-driven issue so much as it's a temperature issue. And you don't mix and match. So if you're going to use, a manufacturer's going to put neodymium iron in, they're going to put it on the outside can, the drive and the driven carriers. And once you get to higher temperatures, neodymium iron will basically magnetically decouple after it gets higher temperatures. And actually, once it starts approaching those temperature limits, it actually will start to lose, or it could start to lose magnetism. So another reason, I think, to stay conservative. If a manufacturer says 350F and you're consistently running 340, you may see degradation. You probably will see degradation of the magnets over time. So for those higher temperature applications, you go samarium cobalt. Samarium cobalt's a 5 to 20% price adder on any given size pump, depending on manufacturer. So it certainly is a little more of a rare material and more expensive, but on those higher temperature applications, samarium cobalt really is the magnet of choice. It is synchronous drive, so there's no, even though there's an eddy current loss when it goes through the can, you don't have slippage, all right? So if your outside magnet is running 1,762 RPM, then your inside magnet, and hence your impeller, is running 1,762 RPM. Containment shells, your containment can. Wide variety of materials. For metal pumps, for metallic pumps, almost always you use a metal can. Again, stainless is a minimum, but typically even with stainless applications, you'll see a Hastelloy can. and then you can get up to titanium or anything else you want. And then with most non-metallic lined pumps, you use a non-metallic can. Regardless of material, the biggest issue is corrosion resistance. Not as much of an issue with the line pump as soon as you're picking the right material for the pump, but you do want to make sure that if you're using a metal mag drive that your can is going to be rated for the chemical that you're pumping from a corrosion standpoint. Metallic can, and this is the biggest issue, in my opinion, with metal mag drives. Metallics have a higher hysteresis loss through the can. And that hysteresis loss, or we'll call it an eddy current loss, manifests itself as heat. So as you send that magnetic attraction across that can, you're imparting heat into the liquid that you're pumping. Whereas most non-metallic cans, I can't really say they have no eddy current loss, but they have very, very little or almost insignificant eddy current loss. So in that case, you're not imparting any heat into the liquid. So who cares? Well, if you're pumping even a toxic chemical, but it's at 75 degrees and the flash point is 230 degrees, and a couple extra degrees put into the fluid doesn't matter, then nobody cares. But if you're pumping a toxic fluid and it's at an elevated temperature and you're very close to the vapor point or the flash point of that fluid, by just adding 2 or 3 or 5 or 7 degrees, now that means that especially if you can't dissipate that heat quick enough, then you flash and you flash back, and you'll flash really basically right across that inside magnet can area, which is a tight connection or a tight space, and then you'll flash all back here. In a sense, then you start running, even though you may be pumping out here you're running dry. And as soon as you run dry, now you're doing two things, right? Now you're generating heat through an eddy current loss, and you're not using the pumped fluid, and we'll talk about this in just a second, to dissipate that heat or to carry that heat out the discharge. So pretty soon your magnets, you're going to have a lot of temperature, your mag's going to grow, and either they're going to, the inside magnet will grow and actually lock into the can, or vice versa on the outside of the driven magnet, and then you're going to lock up and you're going to decouple. And we'll talk about power monitors here in a couple slides. They're a good way to pick that up. So a metallic versus a non-metallic can is a big deal, and I would argue one of the primary drivers over the last 15 years of the popularity of non-metallic lined mag drives. One, certainly it's cost, but two, it's you don't need to be as it has better dry run capabilities, and it's less forgiving on those close to vapor pressure applications. So there's our metal, right? There's our metal containment can. So this shows this is a good view of the outside magnets, right? Runs right around here, and right inside that can there's an inside set of magnets. So that's your metallic containment can. And this just happens to be, again, this is from Inomag, but this is a non-metallic containment can. So I think from an Inomag standpoint, I think it's ETFE inside, and then they use this aramid fiber on the outside. And really all that does is it gives you strength, right? Because this is, the can is your point of no return. So you don't want, all manufacturers have a can whose burst pressure is significantly higher than the actual maximum operating pressure of the pump, okay? So in this case, it has a burst resistance, according to Inomag, of this 3,000 psi. And I'm not sure why the can disappeared off the screen. Okay, bearings. Now, when I say bearings, I think maybe this is the first time I've talked about the bearings. The bearings are right here. So the bearings are typically stationary. They're within the containment can, so that means that they're open to process fluid, and they act like normal bearings do. They are supplying both radial and axial loading. They take the radial and the axial loading from the pump. So this is another. This looks like, I know that it's just a bad picture. These look like they're, a metal. It's just the shine of silicon carbide. Those two happen to be silicon carbide, and that's just a non-metallic spacer. So you have a couple material options. Typically, most manufacturers in this bearing area too. Okay. Carbon is some manufacturers go right to silicon carbide. Some manufacturers offer carbon. Carbon, very resistant to many chemicals, not all, but many chemicals. The one that I know of right away that there's an issue with is sodium hypochlorite. We actually do a lot of business in the water wastewater market, which does a lot of use of sodium hypochlorite, right, different forms of chlorine to disinfect. Carbon's not good for that. From a compatibility standpoint, you have to move to silicon carbide. And there are other materials, there are other chemicals in the chemical, petrochemical, pulp and paper business markets that act the same way to carbon. It's a relatively soft material, so if you do have the propensity to dry run your pump on occasion, which we never recommend you do, you do get a little more forgiveness because you don't get as quick of a heat generation in between the shaft OD and the bearing ID. So you do give yourself a little bit of forgiveness if you temporarily run the pump dry, like a tanker unloading would be an example. But it is, being it is a soft material, then if you do have some small solids, you need to pay particular attention to the quantity and then the hardness of those solids, because it's a tight tolerance between the shaft and the bearing. And even though most bearings are fluted, right, they have little pads that carry fluid and solids across and out of that area. Hard solids will start scoring the bearing, and pretty soon you're going to lose your radial and axial loading capability. The option then is to go up to silicon carbide. It's a more expensive material. It's probably, again, I'd say 5 to 20% additional cost of the entire pump, depending on the manufacturer. Better resistance to almost all chemicals. You know, we stop to say all, but certainly most chemicals. And it's a much harder material. So obviously, if it's harder and you do run some small solids, you've got a much better chance of getting increased life with the silicon carbide as opposed to the carbon. But because it's hard, you get a lot of heat generation. So if you do run dry or you're running a real low flow and you're not getting adequate cooling and fluid back in your bearings, over time you are going to negatively affect your silicon carbide bearing, and it's going to fail prematurely. The bearings do carry a radial and axial thrust, as we mentioned, and again I said it's inside this containment can, so it is all in the process fluid, right? Everything from suction all back here to discharge is all exposed to your process fluid. All right. There's other features, but I just did want to point out jacking bolts. I'm pointing to the jacking bolt right here. This is on a Flowserve metal mag drive. Right, you have a very strong magnetic attraction here. So when you unbolt these, you take these bolts off and you want to pull your power end away from your liquid end in the maintenance shop. If it's a very low horsepower, couple horse, 1, 2, 3, maybe 5, you probably can pull those apart by 2 strong young people. But anything higher than that, the magnetic attraction is strong enough that you can't physically pull them apart. So you actually have to use this jacking bolt to push, and there's obviously, I think there's 4 on this pump. And you screw them all in, and you're pushing against a flat surface here, and you actually start jacking your power end away from your liquid end in your can. And once that magnet right there gets to right about 3/4 of the way off of your inside magnet, the 2 magnets will decouple. Whoops, I'm sorry, guys. The magnets will decouple. More importantly than using the jacking bolts to take the pump apart, because you have to, you need to use the jacking bolts to put the pump back together. If you do not use those jacking bolts in the reverse direction, and you get your fingers, right here, right? You got a hand over here, and you got a hand here, and you're sliding this across. Once you get those magnets about here, this whole power end is going to, for lack of a better phrase, it's going to slam right into the pump because those magnets are going to immediately attract each other. And if your finger happens to be right about there, you're going to have a heck of a time getting that finger out. So every pump manufacturer very clearly lays it out in their instruction manual how to properly take apart and put a mag drive pump back together. And we would urge you to read those instruction manuals because that really probably is the most serious the most serious maintenance concern is using those jacking bolts to put that pump back together. So we have a little bit of a dynamic here, a video here, and I'll show a couple of these slides. But we've talked a lot about the bearing materials and hysteresis loss and heat generation. So every pump needs to provide some form of cooling back in this can area. Right? Here you're fine because you have all sorts of process fluid going through, dissipating any heat that might be generated. But you have much less here, and here are your bearings. In this Inomag example, here are your bearings. So there's where you have your hysteresis loss. And now again, in this pump, it's not as critical because it's a line pump, but you still are going to get some little bit of heat generation there, and you're going to get heat generation right down here. So this red line shows that you have, right, the fluid has already left the impeller, so you have high pressure. So that high pressure comes down, goes in between the can and the bearing, the can and the magnet, and then in between the magnet and the bearing. And this doesn't show up, but you can see that this is a rifle drilled shaft. So there actually is some fluid that goes through your rifle drilled shaft, back out to low pressure, and send out your discharge. So that's just one good visual of how you get I apologize, folks. How you get circulation back into that magnet area. This is the first slide I started off with. I didn't pay attention to the arrows at that time. Now I will. So again, you have low pressure, high pressure, and now you see your recirculation path. And across your can and your magnet, and across your bearings in your shaft, out to low pressure and then back out. Okay. Impellers, Flowserve uses a reverse vane impeller and an open impeller. Gould's Pumps uses an open impeller. Manufacturer Z uses probably one of the two. There's pros and cons to each, but this just shows, again, in most metal mag drive pumps, there is a traditional metal impeller that's used. And in many manufacturers, the same hydraulics that are used for the metal ANSI pump are also used for the metal mag drive. So your hydraulics, your impellers, things like that are interchangeable. For the non-metallic, typically it's a little different. With a metallic pump, the inside magnet, which is right here, okay, in most cases, Inomag, ANSI-Mag, Gould, it's physically connected, integrally molded to the impeller. So what you have behind here, if you remember that video that we started off with, is a series of neodymium iron magnets. Okay. Now, in the case of InnoMag, they actually use a very thin stainless sheath over those magnets. Especially good on chlorine or high chloride applications, okay? And then they cover that with a integrally molded, whatever the material happens to be for that application, pure Teflon, ETFE, Tefzel, what have you. Most manufacturers that manufacture non-metallic line pumps or fully non-metallic pumps do the same thing. I worked for Pulsafeeder. After Gould's Pumps, I worked for Pulsafeeder for about 8 or 9 years. We came out with a non-metallic mag drive gear pump, and it was very similar, where we wrapped the magnets in a Tefzel and now a PVDF coating. It's all injection molded, so there's no welding. There's not multiple pieces of non-metallic coating that you put on each other and then have to produce a weld. It's all roto molded, single molded, so there's very, very little leakage into those magnets. But when you do run a pump, let's go back to our operation. You run a pump drive for, for a low horsepower line pump, it could be an hour, but for high horsepower, it could be 10 minutes. And if you have enough heat generation, those magnets inside there are going to grow, and they're going to grow to a point where they're actually going to pierce this lining, and now you're going to have whatever you're pumping touching your magnets. Your magnet's going to fail fairly quickly, and and then your pump will fail. So it just emphasizes the point to use a power monitor, which we'll talk about next, and do whatever you can to not let your process run dry. So there's a lot of different types of protection for mag drives. There's power monitors, leak detection, amp meters. Most manufacturers kind of recommend power monitors. And you can see here for overload protection, excessive wear and rubbing, bearing failure, decoupled magnets, motor overload. So anytime you see a significant increase or, down below, decrease, and you can set the power monitor to whatever you want, it will sense the high or low horsepower, and then it'll automatically shut the pump off. It's a wonderful if you're running a very steady state process 24/7, you may not need a power monitor. If it's a intermittent application, if it's a suction lift, if it's a tank unloading, if it's just in a plant that doesn't have good operational practices, this is a very inexpensive investment that's going to save a lot of maintenance time and cost, particularly either in run dry or like a blocked suction, a partially blocked suction condition. Last slide, folks. It's 2:35, so we'll probably be done a little early. So, and I'm sorry, I think I might have one other video to show, but there's a lot of different application considerations. I guess the first thing I should have put up there is the fluid that you're pumping. Obviously, again, 70-degree water, you don't need a mag drive. So I'm going under the assumption that if you're toying with a mag drive, you at least have a chemical that, for whatever those reasons on our first or second slide, you meet some of those conditions such that you think you need something other than a single or double mechanical steel. So here are really the three, I'd say, biggies that you need to keep your finger on the pulse of. Number one is solids. Like this company that we represent, InnoMag, they make a big deal about how their design can handle solids, and it actually can. It's a very nice design. It's very unique, and it can handle a higher solids concentration than most mag drives. That said, mag drives are not slurry pumps. So if you have an application that you know there are solids, it doesn't mean you can't use a mag drive, but you really need to understand those solids. These are just a couple of guidelines that one manufacturer uses. But typically you want to know the size of the solid, you want to know the quantity of the solid, and you want to know the hardness of the solid. Right? If you're pumping diamond fragments, you don't need a lot of them to get in between the shaft and the bearing and score the heck out of the bearing, and now you're in trouble. So in that case, hardness is a lot more important than quantity. Right. So solids is the biggest, I'm not going to say red flag, but the biggest area of concern that you need to pay attention to. Viscosity is another one. Typically, if it's a significantly high, if you're doing a significant viscosity correction for any centrifugal pump, like a steel pump, such that a water application would require a 7.5 horsepower motor, and you need to put a 15 horsepower motor on for the viscosity, you would seriously then consider whether it's applicable for mag drive, because obviously once you have that horsepower correction, if you don't adequately size your horsepower on your motor and then also on your bearing frame, you could consistently be decoupling your magnets because you are undersized from a horsepower spectrum. The other thing is viscosity is also a little bit of a challenge when you get back into some of those tight tolerances in between the inner magnet and the can and in between the shaft and the bearings. So viscosity is number 2, and then number 3 is temperature. We talked a lot about, maybe we talked a little bit about the different magnets that you use, and then it's also just the different materials of construction that you use. So if you're at a higher, almost all lined pump manufacturers do not offer samarium cobalt magnets, because once you get above 300, 350, now you are pushing the upper limit of the actual lining material itself. So there's no point in offering samarium cobalt for 500 degrees if your pump can't go to 500 degrees. And then the biggest thing with temperature, again, is how close it is to the flash point and what that temperature rise is inside the can. Folks, that's it. I do not have the other video to show you. I don't know if there's any questions. Let's say I do have a question here. Do the magnets have a finite life that would require periodic replacement? No, not really. Meaning, I would stop short of saying that the magnets have an infinite life, but as long as you don't expose them to excessive heat, you can run magnets for 20 years. I don't think, if you talk to most pump manufacturers, magnets are not a common replaceable part. If you decouple from horsepower, so let's say you don't have a power monitor, you get a big huge slug of something which really puts a drag on your pump, and you exceed your horsepower and you decouple. Well, you clean your pump out, you make sure you have fresh fluid, you start your pump again, and you're fine. You have not damaged your magnets anyway. However, if you decouple due to temperature and you've exposed them to that high temperature, your magnets are done. Move on. You got to buy a new inside and outside magnet carrier. I don't see any other. Oh, I'm sorry. I apologize if you answered this already, but what is the max RPM for these? I don't think I've ever seen a mag drive run above 3,600 RPM. Not to say probably that it couldn't, but most pump manufacturers for small and medium-sized chemical applications start at 3,600 and go down to 1,800. Obviously, I think everybody knows the issue with speed. You need it for higher head applications, but there's a direct correlation between speed and velocity. So over time you will demonstrate a little more accelerated wear in your pump at 3600 versus 1800. But sometimes, if you can run a 13-inch impeller at 1800 and get the same head as an 8-inch impeller at 3600 RPM, and you want to pay the extra cost for that pump, that's great. But 3600 RPM pumps are very, very common in chemical, petrochemical, certainly refining, many other applications. So you can run up to 3600 down as slow as you really want. I don't think I see any other questions. I appreciate everybody's time, and I think you all have the schedule. Frank will be up next in 3 or 4 weeks or so with another mechanical seal market-specific application. Thanks, everybody. Have a great day. I'm sorry, and please call, text, or email if you have any further questions. Thank you.